Welcome to Understanding Power Electronics. This is a series of videos on power electronics. We are on the topic of introduction, and this particular video is on the basic idea behind power electronics. That is, what is the essential idea of power electronics? That's what we are going to see in this video. So let's get started. Let's say we have a load. Load is anything that draws power, and this is a DC load that draws its power at a voltage of V0. Let V0 be 5 volts. So this is 5 volts here, and the V0 value is 5 volts. So the load draws a certain amount of power, and that power is 10 watts we have assumed here, that is PO is 10 watts. And with 10 watts of power at 5 volts, you know that the current drawn will be 10 watts divided by 5 volts, 2 amperes. So the current IO drawn by the load is 2 amperes, DC current of 2 amperes. We have a source, electrical source, a DC power source with a voltage of V in, which is not 5 volts, which we have assumed it to be 24 volts. So the voltage here is 24 volts. So there is a mismatch between the input voltage 24 volts and the output voltage required, or the load voltage required, of 5 volts. Before we go into the basic idea behind power electronics, let us find out what is the problem with a very simple common sense approach to this problem. One of the ways we can simply solve the problem is if we insert something here, so that the 24 volts, we have to reduce it to 5 volts. That means the remaining 19 volts should be dropped somewhere. So we can insert some resistance or something here, so that will drop the 19 volts. So a resistance can be introduced. The resistance develops a voltage because the current of 2 amperes is going to flow through this resistance, and that voltage is VR. And if you go through this loop, we are applying 24 volts. We are having 5 volts here, so the remaining voltage is 19 volts. That should be dropped in the resistance. You can also determine the value of the resistance. 19 volts divided by 2 amperes will be 9.5 volts. So if you take a 9.5 ohms resistor and then stick it there in this gap, it will work. You are dropping 19 volts here. You are applying 24 volts, remaining 5 volts is applied to the load. The load will draw a corresponding current of 2 amperes. Everything works out fine, except, as you can guess, this approach is lossy. Let's see how much lossy it is. Let us calculate the power loss in the resistance R. We are having 19 volts, 2 amperes, so it is 38 watts loss. You can also do I squared R. So 2 times 2 times 9.5 ohms, that will also give you 38 watts. So the power loss in the resistance is 38 watts, whereas the load power is 10 watts. You can see if we are wasting more power than we are using in the load. So if you want to calculate the input power delivered by the source, we can easily do it. It is 24 volts supply. It is supplying 2 amperes. So 24 volts times 2 amperes, that is 48 watts. So power from the source is 48 watts. All right. So you are having 10 watts output, whereas your source is supplying 48 watts. Efficiency is poor. What is efficiency? The output power divided by the input power. That is the efficiency. The output power is PO, input power is P in, efficiency is eta. So you can easily calculate this as 10 watts by 48 watts, that is close to 20%. So it's a pretty inefficient way to do it. Before we go on to see what the basic idea of power electronics is, let us delve into this particular approach a bit more. Suppose the input voltage varies, the 24 volts goes down because the battery is discharged, or the load changes from 10 watts, let's say the load changes to 5 watts. If you take that case, then the current will change from 2 amperes to 1 ampere. 5 watts divided by 5 volts is 1 ampere. The current changes to 1 ampere. You still have to drop the 19 volts here. That means the resistance to be used cannot be 9.5 ohms anymore. It has to be 19 ohms, so that 19 times 1 ampere becomes 19 volts. So you need to change this resistance from 9.5 ohms to 19 ohms. So how do you do that? One way is to use a rheostat, a variable resistance. So I put a variable resistance there, put a person there to turn the resistance this way or that way, all the while keeping an eye on the output voltage. Depending on whether the output voltage is above 5 volts or below 5 volts, you keep adjusting this resistance until you hit exactly 5 volts. Quite impractical. Another way to do it more practically is by doing linear electronics. Here I am showing a BJT or a bipolar junction transistor. This bipolar junction transistor has 3 regions of operation: a saturation region, a cutoff region, and the active region or the linear region. Here the transistor is being used in the active region. That's where, if you are using the bipolar transistor as an amplifier, that's where you will use it. And this kind of approaches are called as linear electronic approaches. Such a power supply, if it is built, it is called as a linear power supply. Now in this transistor, we are aware that we can give a base current under appropriate biasing conditions to make a collector current flow. Yeah? So by adjusting the base current, you can amplify that current and make a collector current flow. The collector current value will be almost equal to the emitter current because the base current will be smaller. So the emitter current is the same as the load current. So what you do here is simple approach. You adjust the base current until you make a current of 2 amperes flow on the emitter side, and that will ensure that the load develops a 5 volts voltage, and the remaining 19 volts will get dropped across the collector and the emitter. Notice that the power dissipation still occurs. The transistor drops 19 volts and a 2 ampere current flows through it. So 38 watts is dissipated. A bit more dissipation will occur because the base circuit also will have some dissipation, but definitely heavy power dissipation occurs. So this way you can control the output voltage to the value that you desire by controlling the base current, and this is normally achieved by a feedback control circuit. Here you see a controller which is sensing the voltage across the load. For voltage sensing, you need 2 points to be connected across the points where you want to measure or sense the voltage. So here, between here and here, you connect the sensor to sense the voltage. The controller takes that sensed voltage, compares it with the reference voltage all through circuits, and then the error is used to drive the base current up or down. If the load voltage is more than 5 volts, the base current will be dropped a bit so that the voltage can come down, the current can come down and the voltage can come down. So through this, the 5 volts is always maintained. This approach is used in linear power supply. Many decades ago, this was the only game in town. All electronic circuits, all electronic equipment had this type of power supply. Nowadays, such linear approaches are not used as much because of the losses involved. However, there are niche applications where a linear power supply is very useful. Linear power supply produces less electrical noise, electromagnetic noise. Because of that, in sensitive amplifiers, in medical applications, in communications applications, where you need to amplify a very low level signal, the power supply has to be noise free, and this approach will be useful. Now we will move on to seeing the basic idea behind power electronics next. Here, instead of connecting a resistance in the loop, we are connecting a switch, an ideal switch. I have replaced a general load with a resistive load because it is easier to explain with a resistive load. That means the resistance RL acts as the load. The value is chosen to be 2.5 volts for illustration. 2.5 ohms times 2 amperes. The previous current is 5 volts. We now see what is the power dissipation in the series switch. So the switch is off and the switch current is of course 0 amperes. So here IO is 0 amperes. So because of that, VO, the output voltage, will also be 0. And because this voltage is 0 and the input voltage is 24 volts, if you apply KVL, Kirchhoff's voltage law, around the loop, you can find that this voltage VSW, the switch voltage, will be 24 volts. 24 minus 0 will be 24 volts here across this. So the switch current is 0 amperes, switch voltage is 24 volts. You multiply the two, you get the switch power dissipation, and that is 0 watts. Very good. So there you had, when you put a resistance, you had 38 watts of power dissipation. Here, when the switch is open, you are getting 0 watts. Now let's close the switch. We have closed the switch here. Current flows through the switch. Ideally, the voltage drop across the switch is 0. Ideally. Practically, there will be some voltage drop, but ideally, in an ideal switch, the voltage drop across the switch will be 0 volts. The current through the switch will be determined by the applied voltage 24 volts and the resistance 2.5 ohms. So it will be 24 volts divided by 2.5 ohms, which will be close to 10 amperes, 9.6 amperes in fact. So that current will be 9.6 amperes. Okay. If you consider the switch, current of 9.6 amperes is flowing, but the voltage drop will be 0 ideally, at least. So the power loss, 0 volts times 9.6 amperes, is once again 0 watts. So when the switch is on, it is 0 watts of power loss. When the switch is off, it is 0 watts of power loss. So switch does not dissipate power. Good. So have we solved the problem? Where's the catch? This is the approach taken by power electronics. You switch, ideally at least there's no power loss while turning on or turning off, than if you stick a linear dissipative device there. So where's the catch? As you can guess, the catch is, yes, we have made the power loss 0, but we haven't solved the original problem. The output voltage, I want it to be 5 volts. Now, when I connect the switch, I get 24 volts here. When I open the switch, there is 0 current, and so 0 volts. Either I get 24 volts or 0 volts, but I want 5 volts DC. So I haven't achieved my purpose yet. So what do we do about it? When the switch is on, the output voltage V0 is 24 volts as noted here. When the switch is off, then the current will be 0, so the output voltage will be 0 volts. So you can switch on the switch for a brief period of time and then switch it off and then go back and switch it on again. So you can do the on off alternately. Then the output voltage will vary between 24 0, 24 0 alternately. Then you can switch the pattern in such a way that the average voltage is 5 volts. The output voltage either is 24 volts or 0 volts, but on an average, you can make the timing such that the average voltage is 5 volts. Okay, I'll show you the waveform. So here the switches can be turned on or off. That double arrow indicates that. So this is the waveform of the output voltage VO. This is the waveform of the output voltage VO. The x-axis is time. When the switch is on, that is the interval T on, and the output voltage will be 24 volts because the source voltage or the input voltage goes through to the load. When the switch is off, that is the interval T off, and then the current is 0, so the output voltage will be 0 volts. So the whole total period T on plus T off is one period of the waveform, capital T or T. It is repeated. So it's a periodic waveform. You are switching at a frequency of 1 over T. Frequency is 1 over period, as you probably know. So the waveform is a periodic waveform switching between 24 volts and 0 volts. Likewise, you can plot the current waveform. When the output voltage is 24 volts, the current will be 24 divided by 2.5 ohms, 9.6 amperes. And when the output voltage is 0 volts, the current will also be 0. So the green waveform here shows the current waveform IO. During the T on interval, it is 9.6 amperes. During the off interval, it is 0 amperes. So it is switching between 9.6 and 0 amperes. Notice one thing, that I have used lowercase letters for V and I in VO and IO. In VO, the V is a lowercase letter. Likewise, in IO, I is a lowercase letter to indicate that these are not constant values or DC values, but instead they are functions of time. They vary with time. Whereas V in is a constant voltage, I have used a capital V. The T on, T off and T values are decided in such a way that the average output voltage, V not average, here V not average, is the 5 volts that we desire. So that is the idea. So while the output voltage swings between 24 and 0 volts, you make sure that the average output voltage is what you want. So we need to find the average of this waveform. So the average is given by 1 over T integral 0 to T V naught dt. In case you are having some discrete quantity, then you sum up all the items and then divide it by the total number of items. So here, instead of summing up all the items, you integrate the voltage waveform. Instead of dividing by the total number of items, we divide it by the actual period of the waveform. The integral is the same as the area of the voltage curve. The area of the voltage curve is 24 volts times T on interval, plus 0 volts times T off. So that is this 1 over T, 24 times T on plus 0 times T off. So that is T on by T times 24 volts. By changing the T on by T ratio, by changing this ratio, we can vary V naught average. So we can control the DC output voltage or the average output voltage by varying the on to total period ratio. So that gives us a degree of control. We are able to play with the output voltage. T on by T ratio has a special name, duty cycle. So V naught average is duty cycle times 24 volts. So we can find out what should be the duty cycle. Please remember the on and off intervals, the total period, etc. is under the designer's control. So we determine what is the value of the D. By choosing the D appropriately, we can get 5 volts here. So D will be 5 volts by 24 volts in this case, 0.208. So by keeping the duty cycle, the ratio of the on interval to the total interval to be 0.208, you will get 5 volts average output. One note, this diagram is not to scale, the waveform diagrams. If this is 24 volts, V naught average doesn't look like it is 5 volts, it's more like it is 10 volts. But I have just drawn the line a bit higher and made the duty cycle a bit larger in order to make the diagram clearer. So the idea is by varying the duty cycle D, that is called as pulse width modulation for obvious reason, the average output voltage can be varied and it can be done efficiently because you are using switching. Every time it is on or off, the power loss in the switch is zero ideally. In practical cases, it's quite low. But have we solved the problem? No, not fully. So what's the catch? The catch, as you can see, is that I'm not getting a good DC voltage. Instead, I'm getting this funny waveform that goes between 24 volts and 0 volts. We would expect a constant DC voltage to be applied to the circuit. From this wavy waveform, we should extract the desired DC voltage out. We can divide the output voltage into two parts. One part is the average voltage that we desire, that is shown here. The remaining is the part that we want to remove. So mathematically, you can write it as VO of T is VO average plus V junk. Junk because we don't need it. It is actually the AC output voltage waveform. It's a function of time. That's why I have written it as VO of time, T. It's varying with time. Now, if you want to find out what is the part to be removed, then we can subtract VO average from the output voltage waveform. So for that, you take the output voltage waveform here and at every instant subtract VO average in a general case. In this particular case, all you need to do is take the VO waveform and push it down by the VO average, that is 5 volts. So that is the waveform sketched here. This is 24 volts, VO average is 5 volts. So this peak here, this one, will be 19 volts. During the off interval, VO is 0 volts. Again, the DC voltage is 5 volts. So 0 minus 5, this will be minus 5 volts. This is the unwanted part of the output voltage waveform which needs to be removed since we want the DC output voltage only. So for this we use a filter circuit. So almost all power converter circuits will use a filter circuit at the output. So now we can summarize the basic idea in power electronics. The basic idea is to use switches because switches cause less power loss. So use switches to vary the current or voltage that you desire in an average sense. You can also use the switches to convert DC to AC or AC to DC. We can also combine. For example, you can use switches to convert from DC to AC, while at the same time you can use the same switches to also vary the magnitude of the AC through pulse width modulation. So you can combine both. This produces, however, unwanted switching waveform that you need to filter out. For that you need to use a filter also. So converter at the basic level will consist of some switches and some filter. There may be other components for various other purposes, but this is about the minimum you are going to see in a converter. Next we will see some examples of power converter circuits. This is a DC to DC buck converter. This is a step down converter. That means the output voltage is less than the input voltage. Both are DC. DC to DC means DC input to DC output. So you can see that it uses a power MOSFET switch, and it also uses a diode. Diode also in a sense is a switch. It's an uncontrolled switch. So this forms the switches part. The power MOSFET is used as a switch. This L and C form the filter. So together this circuit can do DC to DC power conversion. It's a very, very popular circuit. This will be the first circuit which will be analyzed in this series. This is a transformer isolated single phase bridge type inverter. The input is DC. The output is AC, single phase AC. That's why it is called a single phase inverter. This is a bridge circuit. So it's a bridge type of inverter. And we are also using a transformer here. Transformers are used to step up or step down the voltage or current levels. These switches are insulated gate bipolar transistor, that is IGBT, used together with a power diode. This is also a very popular circuit for producing AC output voltage from DC input voltage. It can control both the quality of the AC output voltage and also the magnitude of the output voltage. So you can see, using certain basic components like switches, semiconductor switches, diodes, transformers, inductors, capacitors, a variety of configurations are possible to achieve different functionalities. So during the course of this set of videos, we will be going through a number of such circuits that will form a large part of what the videos are about. With this, we have seen what the basic idea is in power electronics. Thank you. In case you find these videos useful to you and interesting, please do consider subscribing to this channel. Thank you.